Hi class, welcome back again. Today we are looking at a new chapter in Stpm physics. Today's chapter is about static equilibrium, and today for this lesson we're going to focus on the equilibrium of particle. What is static class? Static is the branch of mechanics which deals with the study of body at rest under a number of forces. This is class by Raj, teaching for Physics Form 6 Semester 1. Learning outcome for today's lesson is to state the condition for the equilibrium of a particle and solve problem involving forces in equilibrium at a point. Now class, let's look at equilibrium. Now, with respect to the state of a body, equilibrium may be divided into two categories. One is static equilibrium and two is dynamic equilibrium. Static equilibrium is what? Is a combined effect of all the forces acting on a body is zero and the body is in the state of rest. And if that happens, then we say that equilibrium is termed as static equilibrium. Second, dynamic equilibrium. Dynamic equilibrium is when a body in a state of uniform motion and the resultant of all the forces acting upon it is zero. Then this kind of equilibrium is called as a dynamic equilibrium. Now, the condition for a particle to be in a static equilibrium. Static equilibrium. A particle is in static equilibrium when it is stationary. Okay. Now, the condition for a particle to be in the static equilibrium, that is when it is in stationary, is that there is no resultant forces on the particle. That is the condition. There is no resultant forces on the particle. Okay, this means that the vector sum of the forces on the particle is zero. So if I have a particle here, which is exerted by two forces, which is F1 and F2, then therefore if I look at the vector sum of the forces, F1 is in the positive x direction, so it's plus F1. And F2 is in the direction of the negative, where I can say sum, vector sum, then it's a sum of negative F2 must be equals to 0. Then if this happens, then this particle is to be said that it is in the condition or it is at the state of rest, stationary. Then we can say that the particle is in static equilibrium. Understand what is the equilibrium of particle. Okay, equilibrium of particle. Okay, equilibrium. Now, equilibrium, that means we are talking about static equilibrium. Talking about what? Static equilibrium. Okay, equilibrium, if you see the first sentence is comes from equal. That means equal. It comes from the word equal. Okay, now that means static equilibrium. Static means stationary. Okay, static means what? A particle is stationary. So when we talk about equal, what quantity are we referring to? We are talking about equal forces. Okay, alright. So the condition for a particle to be in a static equilibrium is that there is no resultant forces. No resultant forces that acts on the particle. No resultant forces that what? That acts on the particle. Okay, so in other words, this is the concept for the equilibrium of particle. No resultant forces that acts on the particle, or we can say the vector sum of the forces on the particle is 0. So when I have a situation like this, I have a particle, there is a point, there is a force here which is in this direction F1, and then this direction also somebody is pulling F2. There's two forces acts on the particle. This is particle, two forces F1 and F2. Okay, so there are few ways of explaining this actually. So I'm going to explain it in my own way. So this is in this direction, so we assume that in this direction is positive and then in this direction is negative. So if I sum up, if I total up the forces, I can say positive F1 minus F2 is equals to 0. Because why? They say no resultant forces. So now what I'm doing is I'm finding the resultant forces. So the resultant forces means no. So that means resultant forces, resultant is total force. Yeah, resultant force is equals to 0. So what is the resultant force? F1 minus with F2. So when F1 minus F2 is equals to 0, that means I can say F1 is equals to F2. Okay, F1 is equals to what? F2. Alright. Alright. We get the resultant force is equals to 0. So what is the resultant force in this case? Alright. So it's F1 plus, okay, again I'm going to say F1 plus opposite direction minus F2 is equals to 0. So F1 is equals to F2. Okay, so I get this. Alright. Okay, so what we can say is that first thing, no resultant forces. We can also conclude that since the resultant forces is 0, the component of the forces acting on the particle which in equilibrium must be 0. So in this component is the imaginary line. I will draw an imaginary axis. Okay, like this example. Okay, so this is y-axis and this is x-axis. So I can make a conclusion also that the sum of the component in this example, yeah, the sum of the component of the forces along the OX direction is equals to 0 because it's only OX. There is no forces in the Y. Okay, so let's look at another example. Okay, so if I have like this, I have four forces. This is F1, this is F2, this is F3, this is F4. Okay, so this is y-axis, this is x-axis. So what can I say? First thing, if the particle, this is the particle, it is in static equilibrium. Okay, if it's in what? In static equilibrium. So what can I say? The object is stationary. So the concept says no resultant forces. No resultant forces. Okay, so I need to find the total sum of the component of the y-axis. Okay, which is the sum of the component of the y-axis is upward I take it as positive, downward I take it as negative. So sum of the component is F2 plus, okay, minus F4 is equals to 0. So F2 is equals to F4. Then I look at the sum of the component of the x-axis. This now was y-axis, yeah? Sorry, did I say x or y? Y-axis. This now was y-axis. Now I take for the x-axis, which I assume in this direction is positive, and then here is negative. So I can say, based on this example, I can say that F3, sum of the component plus minus F1 is equals to
0. So F3 is equals to F1. So I can make a conclusion that sum of the components along the OY direction is 0. I can also make a conclusion here. Sum of the components along OX direction is 0. So we know if we solve this kind of questions, we know that the resultant force Fr is equals to Fr square equals to Fx square plus Fy square. So when Fx is 0 plus Fy is 0, so resultant force is equals to 0. Okay, so that means no resultant force. Okay class, that's it. Okay class, I just want you all to pay attention here because this thing did not come out just now in the video. So I have done this. The sum of the component along the OY direction is equals to 0. Then I found the sum of the component along OX where I took F3 positive minus with F1. So if you see here, F3, okay, minus with F1 because it's opposite direction is equals to 0. So F3 is equals to F1. So we can say sum of the component along OX direction is 0. Okay, so that's it. Alright.
Now we know the condition for the equilibrium of particle. Now let's learn how to solve problem involving forces in equilibrium at a point. The first thing you have to draw, class, is to draw a diagram. When you are given a question, if the question does not have a diagram, then you are advised to draw a diagram. As soon as you have finished drawing the diagram, you must determine all the forces that acts on the object of that question. Then you draw the forces on the diagram. Then you apply the condition of static equilibrium in the concept. Then you solve the equation. You have to do this step by step.
Today we are going to look at the first example, how to apply the concept of equilibrium of particle. Okay, so we have a question here. So this question is actually taken from your Oxford Fajar, which you can turn to page 168, example 7.2. Page 168, example 7.2 from your Oxford Fajar book. Okay, so the thing is here, the question says here, a block of weight W, 100 Newton. A block of weight W, which is 100 Newton, okay, is on a smooth plane. Now, smooth plane gives us a information here, which smooth plane means there is no friction force. Incline at an angle 30 degrees to the horizontal. Incline at an angle of 30 degrees to the horizontal means this is horizontal. So this plane is inclined. Okay, so this is horizontal. So this plane is inclined at an angle of 30 degrees to the horizontal. Okay, calculate the value of R1 and F1 when the block is in equilibrium as shown in figure 8. So what we know is, the first thing is, we know we have to draw a diagram. We draw a diagram, but in this case a diagram has already given to us. Okay, so we can skip this step. Alright, now next is we have to draw the forces. Okay, we have to draw the forces that acts on that block. Draw the forces that acts on the block. Okay, so if you look at here, the forces have already been drawn. So you look at these forces here. we have the first force, we have the W, which is 100 Newton. Okay, so this is the plane. Okay, this is the plane and this is the object. First the plane was like this and then the object was here, and then when it was inclined, then the object becomes like that. So W is 100 Newton. Then we have a F1 here and then we have a R1 here. Okay, so what we must do first is that we can draw an imaginary y-axis and x-axis. Okay, like this. Okay, so this will be y-axis and this will be x-axis. Okay, then we see the forces are already given. The forces here are already given. There is a R1. R1 is normal force, and then we have weight here, which is 100 Newton. Okay, so what we do now is we need to resolve the forces that are not in the y-axis and x-axis. Okay, so what shall we do? We resolve the forces that are not in the y-axis and x-axis. Okay, we resolve the forces. So in this case, W is not in the y-axis nor it's an x-axis. So we need to resolve W. F1 is in the x-axis, R1 is in the y-axis. So here we look at this. This will be 30 degrees. Okay, so then when we resolve this, we get here is 100 cos 30. Now why cos? Because the angle to the y-axis, the angle to the y-axis, okay, they are nearer. This angle and this this angle and this x-axis are far apart, so here will become W sine 30. Okay, so I hope you understand that. So here is 30, here is x-axis, so this x-axis will become W sine 30, and the direction, since the direction is outward, so this one also direction is outward, this one also direction is outward. Okay, so here will be 100 cos 30, here will be W sine 30, which will be 100 sine 30. Okay, then we look at this, we just draw. Okay, like this, we make it straight. So we have here R1, we have here F1, and then we have here 100 cos 30, and then we have here 100 sine 30. Okay, alright, so that is all. So in order for the particle, which is the block of weight, to be in equilibrium, okay, what we must do is we must apply the condition where the condition says no resultant force acts on it. No, the condition, no resultant force. Okay, no resultant force. Okay, SULTANT. No resultant force acts on it. Okay, alright, so that means no resultant force means, that means what? This is the condition of the equilibrium. Okay, so what we do is upward force, if we look at y-axis, upward force is equal to downward force. So upward force is R1 is equals to downward force is 100 cos 30. Okay, if we look at x-axis, this is x-axis, left force is equals to right force. Okay, so here 100 sine 30 is equals to F1. So this is the one that is very important, because according to the question, okay, so you see I apply the condition of the equilibrium of a free particle. I apply the condition and I use the condition in this example to get my expression. Okay, So now they ask us to find is the value of R1 and F1 when the block is in equilibrium as shown in figure A. Okay, so now we know we have to find. So this is your maths. So you just 100 cos 30 is how much? 100 cos 30. So you get your answer will be 86.6 Newton. So this will be answer. Okay, so 100 sine 30, 100 sine 30, you will get 50. So this will be your answer. Okay, now let's look at B. The horizontal force F2 required to keep the block in equilibrium as shown in figure B. Okay, so now we have another block with all those forces. Diagram is already drawn. Forces are already drawn. So let's draw an imaginary y-axis and x-axis. So I'm going to take like this. Okay, so this is y-axis. This is x-axis. Okay, so the forces which is not in the y-axis and x-axis need to be resolved. Okay, forces which is not in x-axis and y-axis need to be resolved. Okay, so how do we do that? So here will be 30 degree. And same goes to here will be 30 degree. Okay, it's your maths, yeah. So then now we resolve. Here will become what? Here will become 100 cos 30. Angle and the axis. So this axis will be 100 cos 30. Angle and this axis will be 100 sine 30. Okay, then we also need to resolve F2 because F2 is not in the y-axis and not in the x-axis. So how do we resolve that? Okay, so here will become, because it's inward, you see it's inward, so the direction also is inward. So here becomes F2 cos 30. Okay, and then since this one is inward, here will become F2 sine 30. Because inward, so inward, inward. Okay, like this one example is outward, so I get here outward, and then here also is outward. Okay, now let's draw it. We already resolved it, so let's just draw it and make it more neater. Okay, so this one will be R2, this one will be F2 sine 30, this one will be F2 cos 30, this one will be 100 sine 30, and this one will be 100 cos 30. So we have like this. Okay, alright, so now what we do, we apply the condition of equilibrium of a particle. What is the condition? The condition is no resultant force. No resultant force on the object. Okay, so that means what? Okay, now let's look at y-axis. Upward force is equals to downward force. Upward force is equals to downward force. Okay, so this one is upward, this one is downward, this one is downward. So we get one equation here, which is R2 is equals to F2 sine 30 plus with 100 cos 30. There's another way of doing it. If you don't want to say upward equals to downward, you can take positive R2. You can take like this. Okay, upward is considered positive, yeah. Positive R2, downward is negative. Minus F2 sine 30 minus 100 cos 30 equals to 0. You can also do like that. Okay. Alright, because upward is positive, downward is negative, because downward forces are opposite to the direction is opposite to the upward force. So then here becomes R2 equals to this, you bring the other side, becomes F2 sine 30 plus 100 cos 30. You can also do like that. Okay, you can also do like that. You can also do like this. Upward equals to downward. Alright, so that is it. And then next, we look at the x-axis. The left forces is balanced by the right forces. Okay, the left forces is balanced by the right forces. So we have 100 sine 30 equals to F2 cos 30, because they are opposite direction. Or you can say this side is positive, this side is negative. You can also solve in this way. Okay, so you get 100 sine 30 equals to F2 cos 30. Okay, then it is your maths. Your physics has already finished. This is your physics. Now you go to the next one. To solve the question is to put an answer, a magnitude in the answer. Then you have to do your maths. So here if I do this, 100 sine 30 equals to F2 cos 30. I can have F2 equals to 100 sine 30 divided by cos 30. Okay, so what do I get? 100 sine 30. You can also use tangent, yeah, divided by cos 30. So I get my answer 57.7 Newton. Okay, this is my answer. Because why? Because the question says the horizontal force required to keep the block in equilibrium. So F2 is how much? F2 is 57.7 Newton. Okay? Another example, which is example 7.3 from your Oxford Fajar, page 171. Okay, so here the figure below shows a body S of weight W. Okay, we have body S of weight W. Okay, weight W hanging from a point Q on a string PQR with PQ as horizontal. So we have PQR here and then S. Okay, so in this kind of situation, as we always ask the student, is to draw the diagram. But since here is already we are given the diagram, so we can skip the step. Draw a diagram. We can skip the step. Okay. Alright. So our next step is we have to draw the forces. Okay. We have to draw the forces that acts on the object. Okay, so here we look at this. When we draw the forces that acts on the object, then if I look at here, first thing I have is W. Okay, so here I have is what? Is W. Okay, then here I have is tension. So I'm going to label this as T1 or T2. Okay, then there's another string here which is T1. Alright, okay, so I've already drawn the forces. Okay, so now what I can do is I can draw an imaginary line here which is an y-axis, and then I can draw an imaginary line here which is the x-axis. So I'm going to draw here y-axis, here is x-axis, for me to get a better view of what is, how to arrange the forces. So the forces that is not in the y-axis and x-axis, you no need to resolve. You only resolve the forces that is not in the y and x. Okay, again, the forces that is in the y and the x, no need to resolve. Only resolve the forces that is not in the y and the x. Okay, so we do what? We resolve. So which force we resolve? We only need to resolve T2. So once when we resolve T2, here becomes, since it's upward, since it's what do you call this? Outward, not upward, outward. The direction is outward, so here becomes T2 cos 30, and the direction is also outward. Okay, then here becomes T2 sin 30, and the direction is also outward. So if I draw back all the forces, okay, then I'll get here T2 sin 30, here will be T2 cos 30, here will be T1, and then here will be W. Once when you have resolved T2, you no need to put T2 in the picture, okay, because you already resolved T2. Okay, so now once we got that, what shall we do? The question says, if the system is in equilibrium, what is the tension in the string PQ? So what we know by the concept of equilibrium is that no resultant force. The condition is what? No resultant force. Okay, no resultant force. That is the condition. Or you can say the forces are balanced. Another word of saying it, the forces are balanced. Or you can say no resultant force on the particle. Okay, on the particle or on the body, since here is talking about body. Okay, alright, so that means the upward force is equals to downward force, left force is equals to right force. So let's look at, we solve by y-axis. This is y, this is x-axis. We solve by y-axis. So T2 sine 30 is equal upward equals to downward, which is w, or you can put positive, yeah, which I've already taught you all the last example. Okay, and then we look at x-axis. Left force is equals to right force, or right force is equals to left force. So we get T2 cos 30 equals to T1. Okay, so we got this already. This is physics after we apply the condition of the equilibrium of a particle. Okay, now they ask us to find tension in the string PQ. Okay, tension in the string PQ is T1. Now they ask us to find T1, so we can find T1. Okay, so here is, from here is T2 is W over sine 30. This is your maths, yeah, after this. So you can substitute this inside here. So you get W over sine 30 cos 30 is equals to T1. Correct? Alright. So what does that mean? That means T1 is equals to W over tangent 30. W over tangent 30. Okay, so you got your answer. Okay, alright, so this is the answer. What is the tension in the string PQ? Is T1 equals. So you see, the thing is to apply the concept. You see, when I apply the concept is very important. That's your physics. Then after that you solve, it is your maths. Question will be example 7.4, page 171 from your textbook. A particle O is under the action of three forces. Okay, we have three forces, 16, 16, 16 and 8. Okay, so there are three forces, 1, 16, 2, 16 and 8, the third one. So which is 1, 2, 3. As shown in the figure below. Find the magnitude and the direction of the forces which is required so the particle is in equilibrium. So the concept here, the particle is in equilibrium means, that means no resultant forces acts on the, okay, let me write here. That means what? No resultant forces acts on the particle. Okay, so let's do this. We know the concept already, so let's apply the concept in the question. So we can draw an imaginary line here. This is the y-axis. Okay, we can draw it. Actually, they've already drawn, yeah, but I just want to purposely draw it again. Okay, so here is x-axis. Okay, so the picture here I can have is like this. I'm going to redraw it. Okay, so this is 6 Newton, 16 Newton. This one is 16 Newton. This one is 8 Newton. And that's all. Okay, so F is the direction which is required so the particle is in equilibrium. So here we have another force which is F. Okay, so let's look at the angle. Here will be 30 degree. So the forces that is not in the y-axis and x-axis need to be resolved. So we need to resolve 16 Newton. So here will be what? I'm going to resolve this. Here going to be 16 cos 30 outward. So here going to be 16 sine 30. Okay. Then I'm going to resolve 8 Newton, which the angle 8 Newton is 60 degrees from the horizontal. Okay, 60 degrees. So here going to be 8 sine 60. Here going to be 8 cos 60. Okay, then we also need to resolve f, where the angle of f is theta here. So I'm going to use another color pen, which I'm going to use brown. So here will be what? Here will be f cos theta, and here will be f sine theta. Okay, so now let's look at y-axis. The concept says no resultant force acts on the particle. So upward force is equals to the downward force. Okay, so upward force is what? Is 16 Newton. Is equals to the downward force, all downward direction, yeah. So f sine theta plus 8 sine 60 plus 16 sine 30. Okay, so this one number 1. Then I look at x-axis. Okay, look at x-axis. Left forces or right forces, which one? As long as they are balanced in the y-axis and x-axis. Okay, right forces. So I get what? 16 cos 30 is equals to f cos theta plus 8 cos 60. Okay, this is number 2. Alright, so I solved this. Now it's my maths. So here f cos theta is equals to, so shall we solve this? 16 cos, I want you to solve together with me, yeah. Don't wait here, don't wait there and look at the video. I want you to also take a calculator, and I want you to help me to solve this. So let's do this together and check whether our calculation is correct or not. Okay, minus 8 cos 60. So you get 9.86. I get 9.86 Newton. Then this one I solve f sine theta. Okay, I solve this 16 minus this whole thing. Okay, so please solve and tell me. Write down your answer also. Okay, 16 sine 30. Okay, what did I get? I get my answer 1.1 Newton. Okay, 1.1 Newton. 16 minus, wait, let me check and see. 8 sine 60 is 6.92 plus 16 sine 30. Okay, so I get 14.928 minus 16. So I get 1.07. I actually get 1.07, yeah, 1.07 Newton. So I bring it, I simplify it to 1.1. Okay, but since I think I will just use 1.07, since I use this 9.86. Okay, 2 decimal point. Okay, all right. So then what I should do, I haven't finished yet. Okay, so f sine theta and f cos theta. So here f sine theta is 1.07 Newton. Okay, so next is we can divide f sine theta and f cos theta. Okay, number 1 divide by number 2. F sine theta divided by f cos theta. After that is your maths class. How you want to do it, you can do it. 1.07 divided by 9.86. So sine theta over cos theta is tangent theta. So 1.07 divided by 9.86. So shift tangent, I get my answer is 6.19. So I get my answer is 6.2. Theta is 6.2. Okay, again I do it. 1.07 divided by 9.86. I get 0.1085. Okay, then so on. Shift tangent, I get 6.19, which I'm going to put 6.2. Okay, alright. Then what I shall do, I already got theta. I substitute maybe one of this, I just take whichever. So f cos 6.2 equals to 9.86. So f is 9.86 divided by cos 6.2. So I get 9.92. F is 9.92 Newton. Okay, so the question says, find the magnitude and the direction of the force F which is required so that the particle is in equilibrium. The magnitude is 9.92 Newton and the direction is 9.92 Newton and an angle of 6.2 from the horizontal. Okay, at an angle of 6.2 from the horizontal. Okay, so that is all. So you see the concept, the red color are the concept. Alright, thank you class.